Did you know that you get a great discount on Siemens PLC starter kits when you get a RealPARS Pro membership? Check out the links in the description. Platinum 100, or PT100, resistance temperature detectors are an important part of many process control installations. Accurate and repeatable measurement of temperature is a requirement for many processes, including heating and cooling, chemical reactions, pasteurization, and many others. In this video, I will introduce you to the working principles of a Platinum 100 resistance temperature sensor, describe the physical properties of a PT100 sensor that make it valuable for process control, and describe the ways PT100 RTD sensors can be integrated into a measurement and control system. Resistance temperature detectors, or RTDs, are a class of sensors that change resistance when the temperature of the medium they are inserted into changes. This change of resistance is proportional to temperature and varies in a somewhat linear fashion with temperature. This means that as the temperature increases, the resistance of the RTD also increases. So, if I am able to measure the RTD's resistance, I can determine the temperature. Why is this? It is due entirely to the physical properties of the material from which the RTD is constructed. While RTDs can be manufactured from many metals, including nickel and copper, platinum exhibits physical properties that make it ideal for use in RTD temperature sensors. Let's take a look at the physical properties of platinum. First, platinum is a basic element, with the chemical symbol PT. That is the first part of the designation of the PT100 RTD. Platinum has a molecular weight of 195, which makes it a rather heavy metal with free electrons to make it a good conductor of electricity, although not as good as copper or silver. Secondly, platinum exhibits an electrical resistance that varies in a nearly linear fashion with temperature and has a resistance of exactly 100.00 ohms at 0 degrees Celsius. This is where the second part of the designation, PT100, comes from. Another property of platinum that makes it highly valuable to temperature measurement is that it is quite inert. It does not react with other compounds to any great extent. So how much does the resistance of platinum change with temperature? The purity of the platinum used affects the change in resistance when the temperature changes. The most common PT100 RTD used in industry is one that changes resistance at the rate of about 0.385 ohms for every degree Celsius rise in temperature. I know the resistance of a PT100 sensor at 0 degrees Celsius is 100 ohms, so the resistance I would expect at 100 degrees Celsius would be 138.5 ohms. The 385 factor comes from the equation that approximates the resistance of an RTD based on its physical properties. The equation relates the resistance of the RTD at the temperature being measured to the resistance at 0 degrees Celsius. The coefficient alpha in this equation describes the rate of change of resistance with temperature. For the PT100 RTD I have been describing, if I substitute the resistance values of the PT100 RTD at 0 and at 100 degrees Celsius, I find that the value of alpha is 0.00385. Knowing alpha, I can calculate the approximate resistance the RTD will exhibit at any temperature within its range. The PT100 RTD is often referred to as the P385 RTD. There are platinum RTDs that exhibit different values of alpha, and those would be designated with their respective alpha values, such as with the PT391 sensor. The equation is only approximate, so to know the true temperature at any measured resistance, I will need to consult a published standard table of resistance for a PT385 sensor, like the one shown here. You can find the link to this table in the video description. A PT100 RTD is typically constructed by winding a thin platinum wire around a non-conductive core, which helps support the thin wire. The entire assembly is encased in a sheath to protect the sensor and to give it stability. In industrial applications, RTDs are commonly placed inside protective metal tubes called thermowells. The length of the RTD and the design of the thermowell are design parameters determined by the instrument engineer. PT100 RTDs can be constructed from a single platinum wire, giving a sensor with 2 leads. These leads can be connected to a special I/O card designed to accept RTD inputs, or the leads can be connected to a temperature transmitter, which will output a standard 4 to 20 milliamp signal. In either case, the I/O card or the transmitter will have firmware that will determine the temperature read by the RTD from the measured resistance. The table I showed you before is programmed into the transmitter and the RTD analog input card. In order to determine the resistance of the RTD, a special bridge circuit is used, called a Wheatstone bridge. In this diagram, there are 4 resistors. Resistors A, B, and C are of equal value. The 4th resistor is the RTD itself, and its resistance can be deduced from the voltage measured across the 2 legs of the bridge. This 2-wire RTD design is not very accurate because the platinum leads themselves have an electrical resistance due to the length of the wire and the connection points, in addition to the resistance from the temperature detected at the point of measurement. To compensate for this added resistance, a second platinum wire is added to the sensor at a 3rd lead. This 3rd lead is used to determine the resistance of the lead itself, and the resistance is subtracted from the overall measure resistance to give the true resistance due to the change in temperature alone. These 3-wire RTDs are the most widely used in the industry. Although more expensive than a 2-wire RTD, the added stability and accuracy are well worth the added cost. In this video, I introduced you to the working principles of the Platinum 100 resistance temperature sensor, its physical properties, and how PT100 sensors are used in industrial measurement and control systems. I demonstrated the linear relationship between temperature and resistance for platinum. This property of PT100 sensors makes these sensors reliable, accurate, and affordable for most places that temperature measurements are required. So, the next time you come across a PT385 RTD in the field, you will have a much better understanding of how the sensor works. As mentioned at the beginning of the video, you will get a nice discount on Siemens PLC starter kits when you become a RealPARS Pro member. After signing up, you will receive a promo code that can be used to order a professional Siemens PLC starter kit at a discount price. The PLC starter kit also includes lifetime access to the TIA Portal Basic, which is the PLC programming software to program Siemens S7 1200 PLCs. This means that you'll be able to have both the hardware and the software to learn and practice what you learn in your courses. Go to the RealPARS Learning platform and get your Pro membership now. You can find the links in the video description as well.